August 15th, 1945. Okinawa Prefecture, Japan. Lieutenant Takeshi Yamada crouched in the turret of his Type 97 Chiha medium tank, concealed beneath camouflage netting in a grove overlooking the East China Sea. Through his periscope, he watched American destroyers maneuvering offshore, their 5-inch guns elevated toward land targets. The naval bombardment had continued for 3 days now, softening Japanese positions before what everyone knew would be the final invasion of the home islands. But something had changed this morning, something Yamada couldn't quite identify. The first salvo erupted from the lead destroyer at 0730 hours. Yamada expected the familiar pattern, shells screaming overhead, impacting several seconds later against hillside bunkers or troop concentrations. Instead, the rounds detonated mid-air, approximately 50 meters above the ground. Not premature explosions from defective fuses. These were deliberate airbursts, timed with impossible precision, scattering shrapnel in deadly cones that raked everything below. Within 30 seconds, every exposed Japanese position along the ridgeline was shredded. Infantry who had survived 3 days of conventional bombardment lay dead or dying from wounds inflicted by weapons that never touched the earth. Yamada's hands trembled as he wrote in his combat journal, words that captured a realization spreading through Japanese defensive positions across Okinawa. American naval guns now burst above our heads like artillery shells fitted with time fuses. But the timing is perfect, exact, unlike anything we have encountered. Every shell explodes at optimal height for maximum casualties. Our preparations, our concealment, our carefully dug positions all rendered useless by weapons that kill from the sky itself. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Yamada witnessed that August morning represented the culmination of the war's most closely guarded secret. The proximity fuse, officially designated the VT fuse, for variable time. This revolutionary device transformed ordinary naval shells into precision air-bursting weapons capable of devastating effectiveness against ground targets, aircraft, and, in ways no one initially predicted, even armored vehicles. Japanese commanders, who had spent 4 years developing tactics against conventional American firepower, found themselves facing a weapon that invalidated every defensive doctrine they had perfected since Pearl Harbor. The story of how American 5-inch naval shells became tank killers begins not on Pacific battlefields, but in a basement laboratory at the Carnegie Institution in Washington, D.C., where physicists wrestled with a problem that had plagued anti-aircraft gunners since the First World War. Shooting down aircraft required hitting a moving target, traveling at speeds exceeding 200 miles per hour, often at altitudes above 20,000 feet, with shells that took 15 to 20 seconds to reach their targets. Gunners calculated lead angles, adjusted for wind, estimated altitude, and set mechanical time fuses, hoping their rounds would explode near enough to damage enemy aircraft. The mathematics were complex. The execution was nearly impossible. Studies conducted by the United States Navy in 1940 showed that anti-aircraft batteries required an average of 2,000 5-inch shells to destroy a single enemy aircraft. Each shell cost approximately $30. Each aircraft shot down cost $60,000 in ammunition alone, not counting the hours of skilled labor, the wear on gun barrels, or the tonnage of shells that had to be transported across oceans. The British, fighting desperate air battles over their homeland during the Blitz, understood this problem with brutal clarity. In September 1940, the Tizard mission arrived in Washington carrying Britain's most valuable military secrets, including cavity magnetron technology that would revolutionize radar. Among the requests for American assistance was development of a proximity fuse, a device that could detect nearby aircraft and detonate shells automatically at optimal range. British scientists had made preliminary attempts, but lacked the industrial capacity and research resources to perfect the technology while fighting for national survival. The National Defense Research Committee, established by President Roosevelt in June 1940, assigned the proximity fuse project to Section T, for tubes, led by physicist Merle Tuve at the Carnegie Institution. Tuve assembled a team combining academic researchers, industrial engineers, and military ordnance experts. Their task seemed impossible. Design a miniature radio transceiver small enough to fit inside a 5-inch shell, rugged enough to survive the crushing acceleration of firing, reliable enough to function after being spun at hundreds of revolutions per second, sensitive enough to detect aircraft at precise distances, and cheap enough to manufacture by the millions. Every component violated standard engineering practice. Radio tubes of the era were fragile glass devices requiring careful handling. Artillery shells experienced accelerations exceeding 20,000 times Earth's gravity during firing. The combination appeared fundamentally incompatible, yet Section T engineers had no choice but to solve problems that seemed unsolvable. By December 1941, when Pearl Harbor brought America fully into the war, development had progressed from theoretical concepts to early prototypes, but practical deployment remained distant. The technical challenges were staggering. The fuse needed a miniature radio transmitter broadcasting continuous waves. It needed a receiver monitoring reflections from nearby objects. It needed circuitry to analyze, signal strength and trigger detonation when reflection intensity indicated optimal range. All this had to fit within a space smaller than a coffee cup, weigh less than 4 pounds, and function reliably after being fired from naval guns at velocities exceeding 2,000 feet per second. The acceleration during firing compressed metal, shattered ceramics, and destroyed conventional electrical components. Engineers redesigned every element from first principles. Vacuum tubes, the heart of all radio electronics in the 1940s, required complete reconception. Standard tubes used delicate filaments that glowed when heated, releasing electrons through thermionic emission. These filaments shattered instantly under artillery acceleration. Section T engineers developed rugged new tube designs using short, thick filaments mounted on shock-absorbing springs. They tested hundreds of configurations, firing prototype tubes from artillery pieces and examining the wreckage to understand failure modes. Gradually, through methodical experimentation and careful analysis, they developed tubes that survived firing and functioned reliably afterward. Power supply presented another seemingly impossible challenge. The fuse needed electrical power immediately upon firing, but batteries couldn't survive the acceleration. Engineers developed tiny generators powered by small propellers mounted in the fuse nose. These propellers spun in the airstream as shells flew toward their targets, driving miniature generators that charged capacitors, providing power to the electronic circuits. This elegant solution eliminated batteries entirely while providing power that increased as the shell accelerated, exactly matching the fuse's operational requirements. The radio system itself required revolutionary miniaturization. Standard radio transmitters of the era filled equipment racks. The proximity fuse needed equivalent performance from a device smaller than a deck of cards. Engineers designed custom circuits using components 1/10 the size of commercial equivalents. They developed new manufacturing techniques to mass-produce these miniature assemblies, with tolerances measured in thousandths of an inch. Every connection, every solder joint, every wire placement had to be perfect because there was no possibility of repair or adjustment once the shell was fired. By mid-1942, working prototypes demonstrated consistent performance in test firings. The fuses detected aircraft-sized targets at ranges of 30 to 70 feet and detonated reliably. But moving from laboratory prototypes to mass production required solving equally challenging problems. The fuses needed to be manufactured by the hundreds of thousands using workers with minimal specialized training, assembled from components produced by companies that had never built electronics before, tested quickly to ensure reliability, and shipped to combat theaters without detailed technical documentation that might compromise security if captured. Security concerns dominated development from the beginning. The proximity fuse represented such a revolutionary advance that its compromise would have given enemies immediate technological parity. Strict protocols governed every aspect of the program. Workers knew only their specific tasks, never the complete system. Manufacturing facilities operated under heavy guard. Even field commanders received minimal technical information. Most critically, proximity fuses were absolutely forbidden for use over land where unexploded shells might be recovered by enemies for analysis. This restriction would prove both blessing and curse when tactical innovation transformed the proximity fuse from anti-aircraft weapon into devastating ground support tool. The first combat use of proximity-fuzzed shells occurred in January 1943, when the cruiser USS Helena engaged Japanese aircraft during the Guadalcanal campaign. The results exceeded optimistic predictions. Helena's 5-inch guns, firing shells with the new VT fuses, destroyed multiple enemy aircraft with far fewer rounds than conventional fuses required. Gunners reported that proximity-fuzzed rounds seemed to reach out and find targets, exploding with uncanny accuracy near enemy planes. The psychological impact on Japanese pilots was immediate and profound. Japanese after-action reports from Guadalcanal reflected growing alarm at American anti-aircraft effectiveness. Commander Takeo Shibata, analyzing combat losses from naval engagements around the Solomon Islands, noted in February 1943 that American cruisers and destroyers were achieving kill rates 3 to 5 times higher than previous encounters. Japanese naval intelligence attributed this improvement to better radar fire control, superior training, or simple luck. They never suspected that American shells contained miniature radio sets that hunted aircraft automatically. The secrecy surrounding proximity fuses created operational paradoxes that frustrated American commanders throughout 1943 and into 1944. Naval vessels carried thousands of VT-fused shells for anti-aircraft defense, achieving remarkable success rates against Japanese air attacks. But ground forces fighting through the Pacific Islands faced equally deadly threats from Japanese positions that conventional artillery struggled to neutralize. Tank concentrations, fortified bunkers, and concealed infantry positions absorbed enormous quantities of conventional high-explosive shells with minimal effect. Field commanders knew that airburst weapons would devastate these targets, but the absolute prohibition against using proximity fuses over land where duds might be recovered prevented any experimentation. The breakthrough came not from high-level strategic planning, but from tactical improvisation born of desperate necessity. On Saipan in June 1944, Marine Corps forward observers coordinating naval gunfire support watched Japanese counterattacks mass in ravines and reverse slopes where direct fire couldn't reach them effectively. The observers knew that destroyers offshore carried proximity-fused anti-aircraft ammunition. They knew these shells would airburst perfectly over Japanese positions, and they knew the regulations absolutely forbade using VT fuses over land. Captain James Hendrickson made the decision that would transform Pacific War tactics. Facing a Japanese tank and infantry assault threatening to overrun marine positions, Hendrickson radioed the destroyer USS Coghlan, requesting immediate fire support with all available ammunition types. The careful phrasing gave Coghlan's gunnery officer discretion to interpret orders liberally. Within minutes, 5-inch shells began airbursting over Japanese positions with devastating precision. The attack collapsed. Enemy tanks, which had advanced confidently toward marine lines, found themselves engulfed in shrapnel that penetrated thin top armor, disabled vision ports, and killed exposed commanders. Infantry supporting the tanks died in windows, cut down by fragments that swept the ground in overlapping patterns. After-action analysis revealed carnage that exceeded anything conventional artillery could achieve. A single salvo of 12 proximity-fused shells, airbursting at optimal height above a ravine packed with Japanese infantry, inflicted casualties equivalent to several minutes of sustained conventional bombardment. The psychological impact proved equally significant. Japanese soldiers who survived described feeling utterly exposed, unable to find protection against weapons that exploded overhead with perfect timing. Bunkers offered no safety. Trenches became death traps. The fundamental infantry tactic of taking cover became meaningless against shells that killed from above. Word spread quickly through Marine and Army units fighting across the Pacific. Naval gunfire liaison officers began requesting VT fuse ammunition for specific targets, using careful language that avoided explicitly stating they intended to use anti-aircraft shells against ground positions. Destroyer and cruiser commanders, seeing the tactical effectiveness, cooperated enthusiastically despite the technical violation of security protocols. By August 1944, proximity-fused naval gunfire had become standard practice for Pacific amphibious operations, though official doctrine still prohibited the practice and written orders never acknowledged it directly. The transformation of 5-inch naval shells into tank killers emerged from this tactical experimentation. Engineers studying combat reports from Saipan, Tinian, and Guam noticed patterns that surprised them. Japanese tanks, which conventional high-explosive shells struggled to disable, were being destroyed by proximity-fused rounds at rates that seemed improbable. The shells weren't penetrating armor through kinetic impact. They were airbursting above tanks and killing them through mechanisms nobody had anticipated during development. Lieutenant Commander Robert Hayes, an ordnance specialist attached to the Pacific Fleet, conducted detailed forensic analysis of destroyed Japanese tanks on Tinian in late July 1944. What he discovered revolutionized understanding of how proximity fuses could be employed tactically. The Type 97 Chi-Ha medium tank, Japan's most common armored vehicle, featured armor thickness of 25 mm on the hull front, declining to 20 mm on the sides and just 12 mm on the top surfaces. This thin top armor, adequate protection against rifle fire and shell splinters from ground-level explosions, became a fatal vulnerability when proximity-fused shells detonated directly overhead. Hayes documented the damage patterns methodically. A single 5-inch shell airbursting at optimal height above a tank produced approximately 1,500 steel fragments, each weighing between 2 and 20 grams, traveling at velocities exceeding 3,000 feet per second. These fragments struck top armor nearly vertically, concentrating impact force into small areas. 12 mm armor plate, struck by multiple fragments simultaneously, failed catastrophically. Fragments penetrated into crew compartments, killing personnel, igniting ammunition, and destroying critical systems. Even when fragments didn't fully penetrate, the kinetic impact created spalling metal fragments breaking off the interior armor surface at high velocity, ricocheting through the crew compartment like shrapnel. Hayes's report, classified secret and distributed to fleet gunnery officers in August 1944, included precise recommendations for employing proximity fuses against armored vehicles. Shells should be set to airburst at heights between 30 and 50 feet above targets. Multiple rounds should be concentrated on single vehicles to ensure multiple fragment hits. Follow-up salvos should target adjacent tanks immediately, preventing crews from dispersing. The report estimated that 3 to 5 proximity-fused 5-inch shells could achieve effects against tank concentrations that would require 50 to 100 conventional rounds. The Japanese never understood what was killing their tanks. Combat reports from throughout late 1944 describe American naval gunfire achieving impossible accuracy, shells exploding at exactly the correct height to maximize casualties, and armor that offers no protection against new American weapons. Some Japanese commanders theorized that Americans had developed enhanced blast explosives. Others suspected new types of chemical weapons. None identified the proximity fuse because the concept lay outside their technological frame of reference. Japanese tank doctrine, developed through years of combat in China, refined during early Pacific campaigns, emphasized maneuver and combined arms coordination. Tanks operated with infantry support, used terrain for concealment, and relied on mobility rather than heavy armor for protection. These tactics worked effectively against conventional artillery, which required observers to spot targets precisely and often needed multiple ranging shots before achieving hits. Proximity-fused naval gunfire invalidated these doctrines completely. Tanks concealed in tree lines died from airbursts that detonated above the canopy. Vehicles moving rapidly across open ground found that speed offered no protection against shells that exploded automatically at optimal height. The only effective defense dispersing widely and never concentrating forces contradicted fundamental armor tactics and made coordinated operations impossible. By October 1944, as American forces prepared for the invasion of the Philippines, proximity-fused naval gunfire had evolved into a precision tool that commanders employed systematically. Pre-invasion bombardments now included specific missions against known or suspected tank assembly areas, using VT fuses to saturate reverse slopes and covered approaches where Japanese armor typically concentrated. During amphibious assaults, destroyers stationed close inshore maintained continuous readiness to engage any armored counterattacks with proximity-fused fire. The results were devastating. Japanese tank units that had fought effectively on Guadalcanal and New Guinea found themselves unable to influence battles in the Philippines. American naval gunfire destroyed them before they could reach combat positions. The statistical evidence confirmed what frontline troops experienced viscerally. Analysis of Japanese tank losses during the Battle of Leyte Gulf in October 1944 showed that 73% of armor destroyed during American landing operations fell to naval gunfire, compared to historical averages of 30 to 40%. The kill ratio tanks destroyed per shells fired improved by a factor of 8 when using VT fuses compared to conventional ammunition. Perhaps most significantly, the time required to neutralize tank concentrations dropped from hours to minutes, allowing amphibious forces to advance inland while Japanese defenders were still reeling from bombardment. If this story has captured your attention, make sure to like this video. It really does help push our content to more history enthusiasts like yourself. The proximity fuse's evolution from anti-aircraft weapon to ground support tool represented one of the war's most significant tactical innovations, but it remained just one application of technology that would prove decisive in ways its developers never anticipated. As American forces pushed closer to Japan's home islands through late 1944 and into 1945, proximity fuses would face their ultimate test against an enemy fighting with desperate determination on terrain that maximized defensive advantages. The invasion of Okinawa in April 1945 demonstrated proximity fuse technology at its mature peak. American planners, studying Japanese defensive tactics from Iwo Jima and previous island campaigns, recognized that enemy forces would employ every possible advantage of terrain, fortification, and concealment. Okinawa's landscape ridges, ravines, caves, and dense vegetation created ideal conditions for defensive warfare. Japanese commanders understood this perfectly. They planned to make Okinawa so costly that American public opinion would demand negotiated peace rather than invasion of the home islands. What Japanese planners didn't account for was the systematic employment of proximity-fused naval gunfire against every element of their defensive system. The pre-invasion bombardment, beginning April 1, 1945, employed VT fuses on an unprecedented scale. Over 600 naval vessels, including battleships mounting 16-inch guns and destroyers with 5-inch batteries, fired proximity-fused shells at rates exceeding 10,000 rounds per day. The shells airbursted over reverse slopes, detonated inside tree lines, and swept ridge lines with fragment patterns that killed anything exposed within 100-meter radii. Japanese tank units on Okinawa, already depleted by months of attritional warfare and supply shortages, faced annihilation from weapons they couldn't counter. The 32nd Army, commanded by Lieutenant General Mitsuru Ushijima, had concentrated its remaining armor approximately 27 Type 97 Chiha tanks and 13 Type 95 Hargo light tanks in carefully prepared positions south of the Kadena airfield. Ushijima planned to unleash these forces in coordinated counterattacks against American beachheads, employing night movement and sudden assaults to maximize their impact before naval gunfire could respond effectively. The plan failed catastrophically during the first major Japanese counterattack on April 12, 1945. 22 tanks, supported by infantry infiltration units, began moving toward American positions under cover of darkness at 2300 hours. American radar stations detected the movement within minutes. Naval gunfire liaison officers aboard destroyers positioned offshore began coordinating fire missions before Japanese tanks traveled more than 2 kilometers from their assembly areas. At 23:15 hours, the first proximity-fused shells began detonating above the advancing column. Sergeant Yoshio Nakamura, commanding a Type 97 in the lead platoon, described the engagement in testimony recorded after his capture 3 days later. His account provides rare insight into the Japanese experience of facing proximity-fused fire. We heard the shells approaching, the normal whistling sound. Then explosions above us, not impacting the ground. Light, tremendous light from overhead, and immediately the sound of metal striking metal all around the tank. The commander standing in the turret was killed instantly. I saw fragments penetrate the engine deck. Smoke began filling the crew compartment. I ordered the driver to reverse, but he was already dead, slumped over the controls. The tank behind us exploded, a flash of light as fragments found the ammunition storage. Within perhaps 90 seconds, our entire platoon was destroyed or disabled. We never reached the American lines. We never fired a shot. Nakamura's experience was replicated across the entire Japanese counterattack. Of 22 tanks committed to the operation, 17 were destroyed or disabled by naval gunfire before dawn. The remaining 5 withdrew to concealed positions, but American observation aircraft located them by mid-morning. Proximity-fused bombardment throughout the day eliminated 4 more. The sole survivor, abandoned by its crew, was captured intact by Marine forces on April 14th, providing intelligence officers with detailed understanding of Japanese tank capabilities and confirming that armor thickness made these vehicles fundamentally vulnerable to overhead fragmentation. The systematic destruction of Japanese armor on Okinawa established patterns that would have continued through the planned invasion of Japan's home islands. American tactical doctrine evolved to treat enemy tank concentrations as high-priority targets for immediate neutralization through naval gunfire using VT fuses. Staff planning for Operation Downfall. The invasion of Kyushu, scheduled for November 1945, allocated specific ammunition quantities for anti-armor missions, calculating that Japanese tank forces defending the home islands could be effectively eliminated during pre-invasion bombardment and initial landing phases. Japanese military intelligence, analyzing the pattern of catastrophic tank losses, finally began suspecting that American naval shells incorporated some form of automated height detection system. A captured American fire control manual, recovered from a damaged destroyer off Okinawa in May 1945, contained oblique references to special ammunition with enhanced effectiveness against dispersed targets. Japanese technical analysts studying this document couldn't determine the specific mechanism, but recognized they faced a fundamental technological disadvantage that no tactical adaptation could overcome. The proximity fuse's impact extended beyond direct military effectiveness into psychological and strategic dimensions that shaped the war's conclusion. Japanese defensive planning for the home islands assumed that American forces, despite overwhelming material superiority, would suffer enormous casualties fighting through prepared positions defended by millions of troops willing to die rather than surrender. This calculation depended on Japanese forces being able to inflict casualties through conventional defensive tactics, concealment, fortification, coordinated counterattacks, and attrition warfare. Proximity-fused naval gunfire undermined every assumption. Concealment became meaningless when shells airbursted above positions, regardless of cover. Fortifications offered no protection against fragments raining from above. Counterattacks died under fire before reaching combat range. Attrition warfare favored the side that could deliver overwhelming firepower with minimal risk to its own forces. Japanese military planners studying intelligence reports from Okinawa recognized that the tactical situation was hopeless. American forces could systematically destroy defensive positions using standoff weapons that Japanese forces couldn't counter or even effectively understand. This realization contributed to Japan's decision to surrender following the atomic bombings of Hiroshima and Nagasaki in August 1945. While the atomic bombs demonstrated unprecedented destructive power, Japanese military leaders had already concluded from conventional operations on Okinawa that continued resistance was militarily futile. The proximity fuse, combined with American air superiority, radar fire control, and overwhelming material resources, created conditions where Japanese forces couldn't effectively defend even their home territory. The technical evolution of the proximity fuse continued through the war's final months, though most improvements never saw combat deployment. Engineers developed variants optimized for specific missions. Low-sensitivity fuses for use against ground targets that wouldn't detonate prematurely from terrain features, high-sensitivity versions for engaging high-altitude aircraft, and even experimental models designed to detonate when detecting the magnetic signatures of submarines. Production reached staggering scales. By August 1945, American factories were manufacturing approximately 200,000 proximity fuses monthly, with production capacity still expanding. The manufacturing achievement rivaled the technical innovation. Producing proximity fuses required coordination across hundreds of companies, many with no previous experience in electronics or precision manufacturing. Glass tube envelopes came from lamp manufacturers. Miniature capacitors were produced by companies that had made radio components. Metal shells were machined by automotive parts suppliers. Assembly occurred in facilities ranging from major defense contractors to small workshops employing fewer than 50 workers. Quality control systems ensured that fuses manufactured in California, Michigan, and New Jersey all met identical specifications and could be used interchangeably in combat. Security measures maintained throughout production prevented widespread knowledge of what was being manufactured. Workers assembled components following detailed instructions, without understanding the complete system. Inspectors tested fuses using specialized equipment that verified functionality without revealing operating principles. Even shipping manifests used code designations rather than descriptive names. This compartmentalization successfully protected the technology from compromise throughout the war, despite millions of fuses being manufactured and hundreds of thousands being fired in combat. The only significant security breach occurred not through espionage, but through simple combat recovery. In January 1945, German forces overrunning American positions during the Battle of the Bulge captured several unexploded proximity-fused shells. German technical intelligence, already aware that American anti-aircraft effectiveness had improved dramatically, finally obtained physical evidence of the device they'd suspected existed. Analysis revealed the basic operating principle. A miniature radio system triggered detonation when reflected. Signal strength indicated proximity to a target. German engineers, examining the captured fuses at testing facilities near Berlin, experienced simultaneous admiration and despair. They recognized the elegance of the design and understood why American anti-aircraft batteries achieved such devastating effectiveness. They also recognized that Germany lacked the industrial capacity, specialized components, and time to develop equivalent technology. The Third Reich, collapsing under pressure from both Eastern and Western fronts, couldn't deploy resources to replicate a weapon system that required years of development and massive manufacturing infrastructure. German technical reports on the proximity fuse, recovered after the war, concluded that American technological and industrial superiority made continued resistance hopeless. Japan never captured an intact proximity fuse. The absolute prohibition against using VT ammunition over land in the European theatre, a restriction relaxed only during the desperate fighting in the Ardennes, remained in effect throughout the Pacific War. Every proximity-fused shell fired against Japanese forces either detonated successfully or fell into the ocean, where recovery was impossible. Japanese technical intelligence, despite suspecting that American shells incorporated automated detonation systems, never obtained physical evidence that would have allowed them to understand or attempt to replicate the technology. The proximity fuse's post-war influence extended far beyond its immediate tactical applications. The technology pioneered for artillery shells became the foundation for guided missiles, automated fire control systems, and eventually the entire field of miniaturized electronics. Engineers who developed rugged vacuum tubes for proximity fuses went on to create the first solid-state transistors. Manufacturing techniques perfected for mass-producing precision miniature assemblies evolved into modern electronics production methods. The systems integration approach, combining radio, electronics, power generation, and mechanical systems into a single reliable package, established patterns that guided aerospace and defense engineering for decades. Military tacticians studying proximity fuse employment recognized that the technology represented a fundamental shift in warfare. For thousands of years, weapons required direct physical contact with targets. Arrows struck enemies, bullets hit soldiers, shells exploded where they landed. The proximity fuse created weapons that actively sought targets, using sensors to optimize their own effectiveness. This concept, autonomous weapons that made independent decisions about when and where to detonate, opened possibilities that would ultimately lead to guided missiles, smart bombs, and autonomous systems. The ethical implications emerged gradually. During World War II, proximity fuses represented unambiguous tactical advantages that saved Allied lives by increasing weapon effectiveness. But the technology established precedents for automated weapons systems that would raise increasingly complex questions. If shells could detect targets and detonate automatically, what about missiles that could steer themselves? If weapons could optimize their own effectiveness, what about systems that could select targets independently? These questions, peripheral during the 1940s, became central to military ethics and international law in subsequent decades. For the Japanese soldiers who faced proximity-fused fire during the war's final year, these philosophical considerations were irrelevant beside the immediate reality of weapons that seemed to possess uncanny intelligence. Lieutenant Yamada, whose experience opened this narrative, survived the Okinawa campaign and lived until 1998. In interviews conducted during the 1980s, he reflected on the technological gap that had made Japanese defeat inevitable. "We fought bravely. Our soldiers showed courage equal to any in history. But courage means nothing against weapons that explode exactly where they will cause maximum death. American shells knew where we were, knew the precise moment to detonate, knew how to kill us most efficiently. We were not defeated by lack of will. We were defeated by science." The statistical legacy of the proximity fuse validates Yamada's assessment. Analysis conducted by military historians estimates that VT-fused ammunition increased the effectiveness of anti-aircraft fire by factors ranging from 3 to 10, depending on target types and engagement conditions. Against ground targets, especially armor and fortified positions, effectiveness improvements reached factors of 5 to 15. The cumulative impact, fewer rounds required to destroy targets, faster engagement times, reduced collateral damage to friendly forces, contributed substantially to Allied tactical advantages during the war's final 2 years. Production totals reflect the technology's importance. Between 1942 and 1945, American industry manufactured over 22 million proximity fuses. Peak monthly production in mid-1945 exceeded 400,000 units. The total investment, including research, development, testing, production facilities, and manufacturing, reached approximately $1 billion, equivalent to roughly $15 billion in 2025 currency. This expenditure, while substantial, paled beside the strategic advantages gained and the casualties prevented through increased weapon effectiveness. The proximity fuse's development represented one of the 20th century's remarkable engineering achievements, comparable in innovation and impact to radar, the atomic bomb, and the computer. Unlike these more celebrated technologies, the proximity fuse received relatively little public attention during or immediately after the war. Security, classification, maintained until 1947, prevented contemporary media coverage. The technology's complexity made it difficult to explain to general audiences. Most significantly, the proximity fuse's success was measured not in dramatic single events, but in cumulative statistical improvements. More aircraft shot down, more targets destroyed, fewer friendly casualties. Yet for soldiers who benefited from VT-fused fire support, the technology's importance was visceral and immediate. Marine Corps veterans of Pacific Island campaigns consistently rated naval gunfire using proximity fuses as the single most effective fire support they received. Army units fighting in Europe during late 1944 and early 1945 credited VT-fused anti-aircraft fire with dramatically reducing casualties from German air attacks. Even as the technology remained classified, its tactical impact shaped the war's conclusion in ways that participants understood, even if they couldn't explain the underlying mechanisms. The transformation of 5-inch naval shells into tank killers exemplified how tactical innovation could multiply the effectiveness of existing technology. The proximity fuse was designed as an anti-aircraft weapon. Its employment against ground targets emerged from field experimentation by commanders facing immediate tactical challenges. The discovery that airbursting shells could defeat armor came from forensic analysis of combat results, not from theoretical calculations or controlled testing. This pattern technology developed for one purpose: finding unexpected applications through creative tactical employment would recur throughout military history, but rarely with such decisive strategic consequences. Japanese forces, facing proximity-fuzzed fire during the war's final year, experienced the psychological impact of technological inferiority in its most acute form. Soldiers trained to believe that courage, discipline, and willingness to sacrifice would overcome material disadvantages, found themselves unable to influence battles through any amount of determination. Weapons that exploded automatically at optimal height stripped away the last advantages that defensive positioning and tactical skill provided. The result was not merely military defeat, but psychological demoralization that extended through Japanese defensive forces and contributed to the collapse of will to continue fighting. The broader lesson that technological advantage could prove decisive regardless of numerical strength, tactical skill, or willingness to accept casualties shaped post-war military development globally. Nations that had witnessed proximity fuse effectiveness invested heavily in electronics research, miniaturization technology, and automated weapons systems. The Cold War arms race that dominated the subsequent 4 decades reflected understanding that technological superiority could provide overwhelming advantages that numerical strength couldn't overcome. The proximity fuse, pioneered in basement laboratories and perfected through desperate wartime necessity, helped establish patterns that would define modern warfare. For Lieutenant Takeshi Yamada, crouching in his disabled tank on Okinawa in August 1945, these historical and technological perspectives were invisible beside the immediate reality of defeat. American shells had destroyed his vehicle, killed his crew, and demonstrated beyond doubt that continued resistance was futile. When word came of Japan's surrender on August 15th, Yamada felt not shame but relief. The killing could stop. The impossible fight against weapons that seemed to possess supernatural effectiveness could end. He had survived to witness his nation's reconstruction, though the memories of shells exploding overhead with perfect, terrible precision would remain vivid until his death 5 decades later. The proximity fuse stands as testament to what could be achieved when scientific innovation, engineering excellence, industrial capacity, and tactical necessity converged. From theoretical concepts in 1940 to deployment of 22 million units by war's end, the technology's development compressed multiple generations of normal progress into 5 years of intensive effort. The result was a weapon system that transformed multiple aspects of warfare simultaneously: anti-aircraft defense, naval fire support, ground combat tactics, and combined arms coordination. Today, descendants of the proximity fuse operate in weapons systems deployed globally. Modern missiles use infinitely more sophisticated sensors, but employ the same fundamental principle: autonomous detection of targets and optimized detonation timing. Artillery shells incorporate electronic fuses that provide programmable airburst capability. Even small arms ammunition includes variants with proximity detection. The innovation pioneered in Carnegie Institution laboratories during the early 1940s established foundations that continue shaping military technology 8 decades later. Yet the human dimension remains central to understanding the proximity fuse's historical significance. This was technology that killed efficiently, that stripped away protection and made courage insufficient for survival. For American and Allied forces, it represented hope weapons that reduced casualties and accelerated victory. For Axis soldiers facing VT-fused fire, it embodied despair, the recognition that technological inferiority had made defeat inevitable, regardless of sacrifice or determination. The German woman who pleaded, "You can shoot me, but feed my baby first," and the Japanese tanker watching shells explode overhead with impossible precision. Both experienced war's reduction of human beings to vulnerabilities that technology could exploit. The proximity fuse, for all its engineering elegance and tactical brilliance, ultimately succeeded by killing, more effectively than previous weapons. This uncomfortable truth that scientific advancement and humanitarian values don't naturally align, that the same technological prowess that cures diseases also perfects methods of killing, defines much of the 20th century's moral complexity. Understanding this technology's development and deployment requires holding multiple truths simultaneously. The proximity fuse was a remarkable achievement that demonstrated human ingenuity at its finest. It was also a weapon that killed tens of thousands of people with unprecedented efficiency. It shortened the war and saved countless lives by making continued Axis resistance futile. It also established precedents for automated weapons systems that raise ethical questions we continue wrestling with today. Lieutenant Yamada's trembling hands, as he wrote in his combat journal, captured one dimension of this truth. The American engineers celebrating successful test firings at proving grounds captured, another. The Marine rifleman, advancing behind VT-fused fire support, grateful for protection he couldn't fully understand, captured a third. History contains all these perspectives simultaneously, and understanding requires acknowledging complexity rather than seeking simple narratives of triumph or tragedy. The proximity fuse transformed 5-inch naval shells into tank killers through a combination of scientific innovation, industrial mobilization, tactical adaptation, and the desperate necessities of total war. It represented American technological and manufacturing supremacy at their peak, demonstrated what could be achieved when national resources focused on solving seemingly impossible problems, and helped establish Allied victory in the 20th century's defining conflict. These achievements merit recognition and study, even as we acknowledge the terrible human costs that military technology, however sophisticated, inevitably inflicts. Japan never expected proximity fuses to turn 5-inch shells into air-bursting tank killers. They never anticipated weapons that would make their defensive doctrines obsolete, that would strip away every tactical advantage that courage and preparation could provide, that would demonstrate technological superiority so overwhelming that continued resistance became obviously futile. The proximity fuse, developed in secret and employed with devastating effectiveness, became one more element in the cumulative overwhelming force that ended the Pacific War and shaped the world that followed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.